Good morning, everyone. Thanks for joining our ADM press conference about the 40th anniversary of the Apollo 17 launch to the moon, which was 40 years ago tomorrow. So to start, we're going to have Harrison Schmidt, who's of the University of Wisconsin-Madison, begin. And Jack, as you know, was the lunar module pilot for Apollo 17. Next, we'll have Marie McBride, who is a student contractor for the Goddard Space Flight Center and also an undergraduate student at the Florida Institute of Technology, speak. And third will be Brad Jolliffe, who's a professor at Washington University in St. Louis, and he's also a member of the Lunar Reconnaissance Orbiter team. Jack.
Well, thank you, Mary Catherine. It's a privilege to be here at the meeting, and actually, I guess what's this, West Coast time? Yeah, about 10:22 tonight was our launch 40 years ago for Apollo 17. And I want to mention one aspect of that in a few moments. But first of all, I just want to draw attention to the recent passing of Neil Armstrong, our first geoscientist on the moon, and really an excellent one. Some of you who were at the league meeting recently have seen some of this, although it turns out I had some new thoughts since then. The Lunar Reconnaissance Orbiter that Dr. Jolliffe will talk about here in a few moments has given us high-resolution photographs of the landing sites of the 6 Apollo missions that did indeed land on the moon. And here you see the Apollo 11 site just west of West Crater, which is a bit of an anomaly, but we won't worry about that. That had to do with not really knowing where they were actually going to land. And up in the upper left, you see the impressions of Neil Armstrong's footprints moving around the lunar module. Of course, Buzz Aldrin was there as well, but worked mostly around in the vicinity of the Eagle. Neil was the sample collector and the investigator of various items, including an impact crater just to the east of the landing site, and you see his tracks going out there. He also deployed an early version of the Apollo Lunar Surface Experiments package, a version that was somewhat downsized, but in important ways, relative to the ALSEP that was deployed on Apollo 12 and on subsequent missions. What I wanted to point out to you were the science achievements that came from Neil's activities on the moon that I just outlined to you for you on that LRO photograph. He collected a really very fine suite, a diverse suite of samples, mostly Mare basalts and regolith, what we call regolith breccias. The regolith is the debris layer that covers the moon, and when hit by by impacts, often impact breccias or impact rock. We used to call it instant rock, but I think the community doesn't like me to use that term anymore. And as a result of that collection of samples, we immediately, as soon as they were analyzed and dated, found that the moon was far older than most people felt it was going to be. The only person that I recall of that time that argued that the moon's surface would be very old was Harold Urey, no less. And he turned out to be quite right. The rest of us quite wrong, we had been using an assumption that today's rate of impacts was comparable to those of the past. Therefore, because the Mare basalts were old, and the ones that Neil sampled around 3.9 billion years, the large basins, which are relatively older, based on lunar mapping, are even older. And we have yet to date those the oldest of those large basins, or even some of the middle-aged basins. And so, but the basic thought that came from that was that the early solar system history was recorded on the moon. The moon is a library of that history, and it's one shared by the Earth, and one which on Earth has been almost entirely obscured to us as a result of the very active geological processes that have taken place in the last 3.8 billion years of Earth history. Geochemical constraints on lunar origin were established by these samples, particularly in the isotopic ratios and in volatile depletion of the upper part of the moon, at least the upper part of the moon, and in certain major element issues that we won't go into today. The chemical, age, mineral, eruptive diversity of the Mare basalts was established. There are 5 basalt cooling units in the upper 30 meters of this site as sampled by West Crater. The landing was on a ray from West Crater. 9 separate vesicle assemblages. I won't go into what vesicles are in the rocks, but they are quite distinct in the various samples. And 2 varieties of what we've begun calling pyroclastic glasses. The best known example of that I'll talk about in a few moments is the orange pyroclastic glass from the Apollo 17 mission. The magma ocean of the moon was established as a hypothesis, and a very good one, with fractional crystallization of that ocean producing a layered, apparently layered upper mantle of the moon, and with remelting occurring in order to produce the Mare basalts. Also, it was postulated, as it turns out appropriately, that we had a crust made up of a calcium aluminum silicate called anorthite, and that anorthositic crust was a very important part of the emerging understanding of lunar history. And there is a differentiated source region for basalt, plus a titanium-rich source region. The basalts that Neil sampled were quite rich in titanium compared to what we're used to seeing here on Earth. The solar wind volatile resources in this debris layer or regolith are quite extensive and have become increasingly the subject of interest relative to activities, future long-term activities in space, including going to Mars, as well as the possibility of energy resources being brought back to Earth, namely the helium-3, light isotope of helium. About 50% by analysis of the samples, it looks as if that about 50% of these solar wind volatiles are lost just due to agitation in the process of sampling and in splitting samples for distribution to investigators. Of course, once we had the samples in hand, we realized that there are indeed lunar meteorites, meteorites that have been knocked off the moon, meteors that have been knocked off the moon and impacted the Earth. In the experiment deployment that Neil accomplished, we learned a very high seismic Q of the crust. That is, it tends to conserve energy of seismic energy in it. The moon rings like a bell. Some of you may recall that expression of the time that once hit by a meteor or an impact of some kind, that energy travels around the moon several times, which was quite remarkable, something we had seen only in very limited ways, in very local ways here on Earth. A very low seismic noise from the lunar interior. The moon's quiet. Not much coming there. Later on, we found that there are moonquakes, but not, as I recall, not from the approximately 10 days or nearly 2 weeks of data from the Apollo 11 site. Because of the deployment of what's called a corner reflector by Neil, we begin the process of getting very high precision Earth-Moon dynamics by laser ranging to that corner reflector. So you can see that Apollo 11, had we never gone back to the moon, really set the stage for a great deal of new understanding about this small planet that orbits the Earth. And now what I would like to spend some time with is just to mention one aspect of the Apollo 17 mission that is still, as so many of the aspects of these 6 missions, still in very active analysis and discussion. And that is the orange pyroclastic glass, the orange soil. Just recently, you probably are familiar with the fact that new analytical techniques and new ideas on how to apply those techniques have resulted in the discovery of trace water within the small beads of orange glass, and indeed in the small beads of green glass that came as a result of sampling on the Apollo 15 mission. The existence of that indigenous water that has come from the interior of the moon, really is something that relates very strongly to two issues, two discussion points relative to the moon. One has to do with the origin of the moon, because now the existence of these reservoirs of water and other volatile elements, which we have known about for decades, that accompanied the eruptions of the orange and green glasses. The presence of those reservoirs in the deep interior of the moon have to be accounted for with any idea about the origin of the moon, whether by giant impact or some other mechanism. That is still something that my personal opinion, has not been fully dealt with in these ideas about the origin of the moon. The other issue is that we now have another possible potential source of water that for trapping in the cold traps in the polar regions of the moon. We have, as a result again of LRO experiments, Lunar Reconnaissance Orbiter experiments, we have established that there is indeed water ice in the permanently shadowed portions of the polar regions of the moon. And generally, prior to the discovery of this water in the orange glasses and green glasses, the assumption had been made that that water probably was a result of the redistribution of cometary water that had been vaporized and then reprecipitated as a result of impacts of comets on the moon. Well, now we know that at least 3.5 billion years ago, there was another source of water, indigenous water, from the interior of the moon, which may also be recycled and gradually trapped in part in these polar regions. So that leaves us with really three possible sources of material, of water, for the ice that we have discovered, the LRO has discovered, in the polar regions of the moon. One are the comets, which Ken Watson and Harrison Brown back in 1964 established a theoretical basis for it being precipitated in these cold traps. Two is the possibility of very long-term slow migration of solar wind-produced water in the regolith that has gradually been accumulated in the polar regions. That one's a little more difficult to conceive of, but again, it may well work out that that's another source. And then finally, this indigenous water that we now know exists in the volcanic eruptions some 3 billion years ago. So there's exciting times still afoot with the lunar samples. They're the gift that keeps on giving, and it will keep on giving as analytical techniques improve, new ideas come along, new young people start to look at them with more imagination than we have. And it's really, after 40 years, I sense that there's no diminution of the excitement that one can feel about lunar science, or about what it is going to tell us about the early history of the Earth. And I'll conclude with just a thought about that early history. The first, say, 800 million years of Earth history was one of extraordinary violence, huge impacts occurring on the Earth, some of them, and remember, the Earth's surface was aqueous at the time, almost certainly. And because of the debris that was created by those impacts, very probably dominated by clay mineral species, aqueous clay soup, if you will. And it is within that environment that the early precursors of life were created, and ultimately resulting probably in an RNA-like replicating molecule. So the moon has given us new insights into this period of Earth history that we probably would never have gotten any other way. So all of us who were involved in Apollo are, believe me, very proud of the fact that we've not only learned a great deal about the moon, but we are getting insights into the early history of the Earth that we probably never would have received any other way. And I'll be happy to take questions, but why don't we move ahead with the panel and see what results there. Right, Mary Catherine?
Hello, everyone. I'd first just like to say I'm absolutely honored to have the opportunity to stand up here alongside such distinguished scientists and someone who has walked on the moon theirself, a dream that I one day hope to achieve myself. So it is, I just wanted to start with when every Apollo astronaut landed on the moon, Jack himself also, were part of their mission was to set up the ALSEP, which was the Apollo Lunar Surface Experiments Package. And even though the astronauts were actually on the surface of the moon for only about 300 hours, these instruments, they stayed on and collected data for 5 to 7 years, much more than we could have done just with humans themselves. So one of these instruments was the Dust Thermal Radiation Engineering Measurements Package, also known as the DTREM or the Lirin Dust Detector. And they flew on Apollos 11, 12, 14, and 15. Now, as you can see with the size of it right there, that's it. It's about the size of a small juice box, but it had 3 thermometers and 3 separate solar cells up here. And so the instrument and solar cells are originally used to measure the amount of radiation coming in from the sun. But what the instrument did on the moon was actually measure the damage over time from radiation and from dust. And so if we are ever going to go back to the moon and hopefully use solar cells for power, we need to understand how these work in the lunar environment. And this instrument, though it's very small, it took measurements every 54 seconds for 5 to 7 years, creating an immense amount of data. Now, this might look like a whole bunch of not very exciting, a whole bunch of mumbo jumbo, but that's the point. This is a set of microfilm that was preserved from this instrument through the NASA National Space Science Data System, and it was the only archived information from this instrument. Recently, we found that there was raw binary counts found in the communication streams from this instrument. And all of the other data had been lost over time. And so even though the microfilm was preserved at the NSSDC for over 30 years, it was not amenable for actual scientific analysis because of its size and the way it was preserved. So however, when we combine the microfilm with the communication stream, we were able to use the microfilm as a Rosetta Stone to create a final digital data set for the first time. And so now we can begin to use this data set that we thought had been previously lost for the first time in science. So I would like to present for the first time the first modern digital calibrated record of the Apollo 15 dust and radiation data from the surface of the moon. So we believe that within the next 6 months, we should be able to have this along with the Apollo 14 data publicly available so that scientists can use this lost treasure for scientific analysis for the very first time. As you can see along the bottom, that this is an absolutely humongous data set. It takes up way more room on my computer than one could ever imagine. But here I have just shown you a little snippet of it so you have the opportunity to see that you can tell that there are 3 different lines here, each of those representing the 3 different solar cells. And each of these peaks represents 1 lunar day, with the low points representing the lunar night. And so now we have actually plotted those top lunar peaks of every single day for the Apollo 15. You can see that there's still a large amount of analysis that can be done with this, but preliminarily we can show you a few things. The green covered cell actually shows that there was only minor degradation over time. And then the red pre-irradiated cell, which meant it was damaged by radiation before it actually reached the surface of the moon, shows very little difference. And so we don't believe there could have been much more radiation done to that cell. So it was a good control. And then the blue uncovered cell shows many of the major changes. the most major degradation through this whole set occurs right here, and that is the 1972 solar particle event that actually hit the moon. And so, thankfully, no astronauts were on the moon at this time, but it's believed that an event...
Almost.
But it is believed that an event of this magnitude might have presented a severe radiation hazard. And this is a well-documented event, but with this data set, we can hopefully bring new insight into how the solar flare was felt on the surface of the moon. And so the other thing I'd like to point out is that you see as the covered and pre-irradiated cells, they come together pretty much at the end. That is, you can draw the conclusion from that radiation was the major degradational factor on this instrument. So another thing that's exciting and able to show is there's actually eclipse data in here. An eclipse on the moon happens that when the Earth comes in between and blocks the sunlight from reaching the surface of the moon. Therefore, you can see that there's just an instant drop in the data received there. And so you can go through the data set and actually see where the eclipses took place that match the ones that have been recorded that we assume would be there. And so finally, I would like to end with a picture of the Apollo 15 landing site. And so you can see that there is still you can still see where the ALSEP is there, and you can see the tracks that are made by the rover that they had during the Apollo 15. And you can see, since you can still see them, it does prove the point that probably radiation was the greater factor to this instrument than dust, because it's still possible to see the ALSEP in that picture. And so it's a pleasure to be able to give this talk, because I've worked for 1.5 years, and along with my mentor, Dave Williams, down there, and as part of the Lunar Data Restoration Project to achieve this exciting data. And so it's now that a full 40-year-old data set can be restored for the first time and be properly archived, and we have the opportunity to analyze it with modern technology for the very first time. And so if we hope to one day return astronauts to the surface of the moon for extended missions, it's imperative to understand the long-term effects of the lunar environment from the instruments, the only instruments to call the lunar surface their home. Thank you very much.
Oh, 40 years has been way too long. We need to go back to the moon. I'm going to tell you a little bit about some of the recent results from the Lunar Reconnaissance Orbiter, which is currently mapping the moon. The Lunar Reconnaissance Orbiter's mission really was to collect information and data that would pave the way for the next generation of lunar exploration, especially human exploration. It turns out that along the way, in addition to all the wonderful images, very high-resolution topography, radiation information that we're collecting, there's a lot of good science. And I'm going to tell you about one of the very interesting science results from my perspective. But what you're looking at here is the background is the Lunar Reconnaissance Orbiter camera, actually the low-resolution camera, which has given us the best ever global mosaic, very good for looking at topography and features of the moon. And then superimposed on that are a handful of locations that have been characterized by the Diviner lunar radiometer. This is an infrared instrument that has a sensitivity to silica-rich materials. And so this is pointing out just about a half dozen sites on the moon that are enriched in silica-rich volcanics or rocks of some sort. Now, we've known for years that these are anomalous spots, but we really didn't know what they were until we got the Lunar Reconnaissance Orbiter in action. Now, we have a hook back to Apollo because you might say, well, what's important about silica-rich rocks and what are they? Well, you are familiar with granite and rhyolite. These are common rocks on the Earth's continental crust. but they're very rare on the moon. We do find some, however, and what you see here in the lower right is about a hand-sized sample of granite from Apollo 12. This is also one of the very important rocks that were returned from the moon that helps us understand this. We really don't even have a clue about this material from the meteorites, so it's the Apollo samples, truly the gift that keeps on giving. Well, these are just found as small bits and pieces of rocks in regolith and in a few breccias, so we really don't know much about how they form or where they come from, but these identifications by diviner really help us perhaps to understand that. You see one of those spots on the left on the near side image is Aristarchus crater. That crater may have struck one of these locations and actually distributed these kinds of materials at quite some distance, even to the Apollo 12 site, which is not that far from Aristarchus. But you see other sites there. And the one on the far side, the Compton-Belkovich site, now this is a new one. This is one that we knew about that was an anomalous area from the Lunar Prospector mission, but we really didn't know what it was until we got Lunar Reconnaissance Orbiter results. And here's an image from the high-resolution, narrow-angle cameras on LRO showing a beautiful ancient volcano that sits in this area of Compton-Belkovich. Now, this is the kind of discovery, two kinds of discoveries I'll mention here. One is where you look in the telescope, you see something. In this case, we look at the image and we say, wow, look what's there. That's a volcano. That's what this is all about. The other kind of discovery comes a little bit more slowly as we sift through all of the data that we have and really try to understand this and figure out how it formed. Just for scale, that's about 2 kilometers across at the top. A beautifully preserved geologic structure. So this is the second kind of discovery where we've looked at a lot of data now. We've looked at this from different angles. You see on the left-hand side there's the entire volcanic complex. It's about 35 kilometers across. And on the right-hand side is topography. The topography is derived from the wide-angle camera data. This is work that was published just this year by one of our colleagues in Germany at DLR. And you can see the topography, the red areas are the high spots, and the dark red splotch in the upper right there is that volcano that I just showed you. So one of the interpretations we can put onto this when we work through the high resolution narrow angle camera data and the topographic information we can glean from it is a cross section. So you see an interpretive cross section at the top there. Our interpretation now is that there are volcanic constructions on the flanks of this area and to the north, and in the center there's a collapsed area. This would have been above the magma chamber as it emptied and produced the volcanic construction. This is a feature that's relatively common on Earth. We know this kind of structure. Now, we can take this a step further. Now we get into some speculation, but we try to understand how this formed. Why is it out there all by itself in this part of the moon? Well, our current thinking is that heating deep in the moon produces something like basaltic underplating, may cause partial melting. There may also be a mantle plume that comes up and brings heat into the crust, causes melt. That melt works its way into fractures. The lithostatic load, the pressure from above, drives that lava up toward the surface. It's not enough to break through the surface, but when it gets close, it forms a dome. Fracturing, ring fracturing leads to volcanic eruptions, and then late-stage magmatic fractionates, granitic-like material, then extrudes to the surface. So this is the way we go about doing this, and this is the sort of the tertiary kind of discovery where we really worked through this. Of course, now, for those of you who heard the GRAIL results yesterday and you're looking at the numbers and the densities up there, you realize that I have to go back to the drawing board because we now think those densities are probably a bit too high. So this is kind of the way things go. I'm going to end, Jack and I didn't talk about this, but I'm going to end the same way he did. Every now and then, we are fortunate enough to turn the camera, the high-resolution narrow-angle camera, back on Earth, and this is the kind of image that can be constructed from that. It reminds us that one of the reasons we do planetary science and lunar science is really to better understand our own Earth. And these observations that we've made on the moon actually give us some keen insights to the earlier period on Earth where we really have no rock record of very, very little material to look at. And understanding how these silicic materials formed will help us understand how they may have formed and contributed to the early continents of Earth. So I'll stop there, and I think now we have time for questions.
Questions?
Hi, Irene Klotz with Reuters and Discovery Channel. Could any of you maybe take a stab at explaining why the discovery of the trace water in the volcanic glass beads, or how that impacts the theories of the big splat that the moon came from pieces of Earth, as far as bolstering it or having a little bit more explanation to do about it?
Well, since I raised it, let me take a first crack at that. We've known for decades that the pyroclastic glasses, the green and orange glasses, were unusual relative to the other rocks of the surface of the moon, sampled at the surface of the moon, in that they were rich in elements that we consider volatile: chlorine, fluorine, tellurium, zinc, sulfur, things like that. That's been known for a long time. It wasn't until the new techniques were applied to the interior of individual beads that the water actually became part of that suite of volatile elements and materials that apparently were part of the eruption, the volcanic eruption of these pyroclastic glasses. Even before the water was discovered, I think the question had to be asked is, how do volatile elements survive the extraordinarily high temperatures, 6,000 degrees Kelvin or more, that the models, now I emphasize that and italicize models, that the models say that the material produced by the giant impact reached. At those temperatures, one would have had expected that, in the simplest view of things, that the volatiles would have dispersed into space. Now, it doesn't mean that they did. It means that the models now have to, in my opinion, have to go back and try to figure out a way in which you preserve some volatiles in certain parts of the interior of the moon, so that at some later time they can be part of these pyroclastic eruptions. I am a skeptic about the giant impact, I will admit that, but still it is a hypothesis, and it's a hypothesis to be tested. One alternative is some mechanism for just capture of an independently accreted planetary body, roughly co-orbital around the sun with the Earth, so that it had the same isotopic composition as we know it, at least in some aspects it does, particularly with respect to oxygen isotopes, and that it also, though, had a protocore, an early large core of chondritic material, stony meteorite-like material, that in itself contained these volatiles. And they could be, then would be reactivated by a process we can discuss later if you're interested, to become part of these volcanic eruptions some 3.5 to 3 billion years later. Is that reasonably clear?
Maybe you could just talk a little bit about what evidence would prove or disprove that theory, and or the what else can be done to kind of choose between these various models of how the moon was formed.
Two things I think would be helpful. One is to put at least as much modeling energy into capture as has gone into the giant impact. Capture has tended to be discarded by the modeling community because it seems at first blush to be a sort of a one-time possibility, that even though some of the satellites of other planets may well have been captured, it has just been ignored. And I think a significant effort ought to go in to see what are the possibilities and what are the parameters necessary to capture a body that is co-orbiting with the Earth. Now, I have to acknowledge that back in 1972, two Swedish researchers, Alfven and Arrhenius, with back-of-the-envelope calculations, came to the conclusion, this is before computer modeling was even thought about, came to the conclusion that capture of a co-orbiting body was inevitable. Now, you also have to consider the fact that the giant impact is an impact-assisted capture, so that comes into the picture as well. So both of them are capture. One just happens to use an impact as a way of assisting that capture. The other thing is that there are vast areas of these pyroclastic glasses that would, if sampled on the moon, would probably give us additional information. And the South Pole Lake and Basin may well have penetrated or excavated deep enough into the moon to give us information that ultimately, if sampled, would feed into answering this question. It is one of the more exciting issues inside there. Just in the last couple of science magazines, there have been some new ideas about giant impact and how it relates to the moon. There's a proliferation now of ideas related to how the moon may have formed, including forming from what one investigator believes is an inevitable planetary disk, that all planets start out with a disk of debris around them. And when you get outside what's called the Roche limit, where inside of which tidal forces disrupt any aggregation of that debris, you get outside of that in terrestrial planets like the Earth, you can develop a moon. Now that's just another hypothesis. In fact, I resist the use of theory for any of these. I don't think you should use that word. They're all hypotheses that need to be tested by as best we can, and with good imagination, we'll think of ways to test them. Brad?
Rick, do you want to ask your question?
Yeah.
Brad, did you want to comment?
If I might, I would just say very, very briefly, we've heard a lot of reports, and it almost sounds like water everywhere on the moon. I just want to remind everyone that the water concentrations we're talking about are really just, it's hydrogen we're talking about, and the concentrations are still pretty low. And as a geochemist, I would say that even in a giant impact, you deplete the volatiles, but you don't completely get rid of them. So I think that's the case, but otherwise, yeah, that's all I would add.
Rick Lovett, freelance. We sat in this room yesterday and we saw these wonderful pictures from, that Grail just brought back. And I would love to see if there's a way to correlate the new stuff. I mean, you did a little bit of this, but I think this question is for Dr. Schmidt. To correlate the 40-year-old stuff with all these spectacular imaging results that we're getting today, how do you feel that all hangs together?
Well, it hangs together with people like Marie here, young people getting involved as they have been, along with the folks that still have a memory of Apollo, like Brad and myself, and doing exactly that, of correlating the new information with the old. Frankly, I think, my imagination on this is probably limited, just because I've now reached the ripe old age of 77. But I think that's what it takes. It takes teams of people getting together and sitting around a table and trying to think about how the new data relates to what we have in the old, and to make sure we're using all the old data. That is one of the things that happened to us after Apollo, is that the funding disappeared, the data started to disappear, and for a long time we were afraid that it had indeed gone, that we weren't going to get to it. We had a session at ASU a couple years ago on the seismic data, and there were people who were really worried about the fact that some of that data was not going to be recovered. We're making progress in that, and we're also making progress, imaginative progress, on how to get that data into actual working form. That's just going to take time. That's one of the reasons why this, I think, lunar science community has been so dynamic for 40 years, is that people come up with new ideas, they come up with new analytical techniques to apply to test those ideas, and it is really going to continue indefinitely, as far as I can tell. And of course, we have slowly increasing numbers of lunar meteorites in which to expand our database.
We have a question from our web chat now from Leo Enright. For Brad, can you talk more about how early GRAIL results will support the LRO?
So the question is how early GRAIL results will support the LRO.
Correct.
There's one thing that's really obvious is understanding the gravity field of the moon really helps us in terms of orbiting and the orbital dynamics. So working out these variations in gravity, which is key to being able to safely orbit the moon, is a very, very strong result. And I think we have, from LRO, we have the best topography, and so we really understand the topography now, and that's come largely from the laser altimeter and from the cameras from which we derive topographic data. And that, I think, meshes very well with the gravity. In fact, all the gravity results you saw from GRAIL draw upon that correlation between topography and gravity. And also, some of the really new, exciting results are things like the density of the upper crust, the porosity through the upper crust. This really helps us to understand what's going on under the surface.
Jonathan Amos, BBC News. Question, I think, for Jack. Given what we know about the moon now, state of knowledge, if we could put a geologist back on the moon, you know, boots on the regolith, where would you want to send that geologist, and to address which particular pressing issues at the moment, do you think?
Well, that's a tough one, but I think right now I would, in prioritizing potential future landing sites, I would probably say, with a lot of planning and thought beforehand, going to South Pole Aiken with significant mobility. I'm not absolutely sure what you'll get from one spot in South Pole Aiken. I think you probably need significant mobility and time in order to examine a variety of features. But I have not done any kind of mapping, for example, South Pole Aiken. Others have begun that process and been involved in that. And it would take that kind of analysis to decide exactly where you would want to land and where you would want to go once you were there. It is the most unusual, as yet unexplored part of the moon, and one which has, because it's 12 kilometers below the mean lunar radius in depth, it has a tremendous potential, because the transient crater almost certainly was even deeper than that. I mean, it was a serious impact on the moon, and I think there's one other very serious impact on the moon, and that's the Procolarum Basin. And some new data on pyroxenes is suggesting that it sort of raised that issue again. But Procolarum is so old and so damaged by other impacts that I think it'd be very difficult for a one-time mission to some part of Procolarum to come up with a conclusion of whether of any as meaty as South Pole Aiken would. Now, you may or may not be aware that when there was still a question about where Apollo 17 would go, I raised the possibility that we should go to Tsiolkovsky. Well, Tsiolkovsky would be very interesting. It's a pretty good-sized basin, and you could reach both the central peak of Tsiolkovsky and the rim with a Apollo rover-type mission. You could have had communications with a satellite placed behind the moon and a libration point station keeping there. But that was a little bit beyond the risk-taking capability of NASA at the time. And I was we had worked it out. We'd worked out pretty much what you'd have to do, but then that was discarded. And I think we picked, on the near side of the moon, I think we picked one of the best places to go. And from a three-dimensional point of view relative to the geology you could see, Taurus Littrow was really spectacular.
What issues would South Pole Aiken address?
Well, South Pole Aiken would address, I think almost certainly, the lower crust, possibly upper mantle characteristics. It would probably, again, properly planned, start to give us ideas on why the distribution of this so-called creep rock, potassium rare earth element phosphorus-rich rock and thorium and rich rock is concentrated on the other side of the moon. There's a little bit of anomaly in South Pole Aiken, and it may be South Pole Aiken reached down to the level of the original magma ocean where this type of material was accumulating due to a process that Brad mentioned earlier, the fractional crystallization, where these kinds of elements, they're called incompatible elements, tend to concentrate in the last melt that's left when you start to crystallize a very large body of magma. And that I think South Pole Aiken has the potential of giving us that kind of insight, at least, into how that material ended up being concentrated on the other side of the moon, as far as we can tell, in the region of Procol Harum.
May I add briefly to that?
Go ahead.
Just very briefly, and Jack knows this, I'm an advocate actually of a robotic exploration to South Pole Aiken Basin, and one reason for, and in addition to all the things that he said, there's the opportunity to get materials that we can use to date the basin. It's the oldest, largest basin on the moon, the oldest, very well recognized one, and actually there are other basins and large craters within it. We can determine the chronology of this basin and test the solar system cataclysm hypothesis. And so that's another very strong reason for going back, in addition to all the things it will tell us about the moon.
And it's my understanding, I haven't read the paper yet, but that some of the recent modeling relative to the cataclysm hypothesis is now making it look like that the cataclysm may have been episodic. And Brad's exactly right. A date, an age date of an impact melt breccia clearly identified with South Pole Aiken would be very, very important. And I say melt breccia clearly identified with South Pole Aiken. That's part of the planning process. Where would you go in order to get there? We think we have impact melt breccias from Serenitatis and Imbrium, but you'll find people, including myself, who really list that as a hypothesis, because we're dealing with boulders, we're dealing with individual rocks, and until you can get enough statistics on these things, it's really hard to be absolutely sure that you have dated basins such as Serenitatis and Imbrium. We think we have. We use that as a working hypothesis, but there still is that element of doubt. So planning is very important on these to go to the right place to get those kind of dates.
We have one more question for you, Jack, before we have to wrap it up, and this is a question from Leo Enright from Irish TV, and he's hoping you can just give a few words, comment on the anniversary of the Apollo 17 launch tomorrow.
Well, there are 2 weeks of transcripts that cover that remarkably well. Apollo 17 was, unfortunately, in my opinion, the last of our, at least the most recent of our missions to the moon. It was a great honor and privilege for me to participate in that. You have to realize that there were some 450,000 Americans that were involved in the Apollo program, and that they were almost entirely young people. The average age of engineers, scientists involved in Apollo was roughly around 25. And we tend to forget that, particularly as we get older. The astronauts, for example, were among the older people in the program. We were generally in our 30s. The middle-level managers were generally in their 30s, early 40s. And it really was a young person's program. And if you, in thinking about the 40th anniversary of Apollo 17, I think about what would it take to go back to the moon, to prepare to go to Mars. And it's going to take a lot of young people getting involved and having an organization where it's capable for those people to participate. That is going to be a challenge for any time we set up a new deep space program such as Apollo for geopolitical or other reasons. We have to design it so that it can, through multiple generations, stay young. I would mention there is an organization that has done that in the United States, and it's called the Nuclear Navy. And they have figured out right from the beginning how to stay young. And that's extremely important. And maybe that's a model we could look at and see if there's a way to do that within the civil service so that you can indeed tap the motivation, the imagination, the stamina, and the courage that young people bring to a program. If nothing else, they haven't learned how to fail yet. And that's an extremely important psychological aspect. And if you just look at Apollo, nobody believed that we would fail. And that's the way we operated, that it could be done, and indeed was done. So Apollo 17 just put a capstone on that. It added, I think, a great deal, but it added to a tremendous base of knowledge that had been developed on the previous missions. I just outlined one of those, namely Apollo 11, and what it contributed. And each of the missions, you can come up with a similar list of contributions to our better understanding not only of the moon, but as Brad has indicated, our understanding of the early history of the Earth. We would not be debating whether or not these large, very large impacts on the Earth created melt sheets that differentiated, that is, crystallized fractionally today if we hadn't brought back samples from the moon. And the fact that we now see within certain, one particular mineral that we find in the very old rocks of the Earth, namely zircon, zirconium silicate, age dates that relate back to this very early history. The oldest zircon, I think, now is 4.4 billion years old. You have to ask yourself, how did these things develop? Because they don't really come into existence unless you differentiate a lot of magma, because zircon is not a very abundant element and it's incompatible. It's only in the very last stages that it combines with silica to form zircon. So these are exciting things, and they've been exciting for 40 years, and I suspect they're going to be exciting for at least another 40 years.
Thank you so much to the panelists. Our next press conference is at 9 a.m. We're going to delay it a few minutes on the Anthropocene. We'll get started shortly. Thank you.